this over here. All right, gotta reverse that. Game display capture. Oh no. Oh no. Where'd it go? All right. Why is that not working? Why? Okay. Come on. Bloody hell. So where'd it go? Bear with me. I'm trying to fix something. Why does it keep doing this? Where are you? This is working perfectly fine. Add display capture. Okay. Okay. We'll get going here in a second. Okay, display capture. Transform. Horizontal. There we go. Alrighty. Alright, file settings. Hotkeys. Okay. Alright, that should fix it. Let's see. Yes. Okay. Hey, what's up, Jacob? Give me about 5 minutes. I've got to, the technical difficulty slowed me down. I'll be right back. I just got to use the restroom. Can everyone hear me? All right. So, hope y'all are doing okay. Let me just hit record here on OBS. Alrighty. All right. So, hopefully y'all had a chance. Oh, come on, man. To take a look at the notes for why is that not working all of a sudden? Take a look at the notes for the okay, there we go. Take a look at the notes for resonance. If not, that's fine. It's kind of a standalone lesson, so you can always go back on YouTube, look at that. It's only about 20 minutes. So I think I left here at the last recording. Now, in this case, we got ourselves a rope hangs down from a high tree branch at the edge of a river. Josh, who has a mass of 65 kilograms, trots at 2.5 meters per second to the edge of the river, grabs the rope 7.2 meters below where it is tied to the branch, and swings out over the river. And we want to know what the minimum time that Josh must hang on to make it back to shore. Well, first off, and again, if you have questions, jump in on chat. If we want to know the minimum time that it's going to take him back to shore, right, he's going to have to swing from here to the maximum displacement over here, and then back to equilibrium position. Right. So if we're looking at in that case, well, what's the time it takes for him to go from here to your maximum displacement and then back down to equilibrium? Well, each section here, right, if we think of his action like a pendulum motion, right, each motion here, or each time period here, would be 1/4 of the period, right? So 1/4 of the period is for him to swing up here to your maximum displacement, and 1/4 of the period to come back down here to equilibrium position where he'd be safe at shore, right? So if we're looking for finding that time that it's going to take for him to reach shore safely, right, he's going to have to hold on for half of the period. So recognizing that this kid swinging on this rope right here is acting like a pendulum, well, we can just use the pendulum equation to solve out for the period, right? So, and I'm going to have to do this kind of a janky way, but that's fine. Right? If you've got yourself, oh God, it's backwards. I knew it. Give me 1 second. Logitech transform flip horizontal. Okay. All right, you start with your period of a pendulum, right? T equals 2 pi L over G. Case, right? The period is what we're solving for. 2 pi. We know that the length of that rope is 7.2 meters over G, which we can assume this kid is on Earth, right? Meaning that G would be 9.8 meters per second squared, right? You solve that out and you get that, let's see, 2 pi, let's see, square root of 7.2 over 9.8 times 2 pi. We get ourselves a period of 5.4 seconds, right? So 5.38 seconds. So if we're looking for the time it's going to take for him to get to shore, right, it only takes half of the period for him to swing up here to maximum displacement, to his maximum amplitude, and then back down. So divide that by 2, and you get a time of 2.7 seconds for him to safely reach shore. It's still backwards. Awesome. Are the notes backwards? It shouldn't be backwards still. That shouldn't be backwards, right? Both are now. Good God. Okay, give me 1 second. Because what YouTube is showing me must be flipped from what you're seeing. It's like YouTube should just show me the same thing you guys are seeing. Flip horizontal, okie dokie. Oh god, alright. Flip horizontal, okie dokie. Good now? Okay. Let's see. Oh, and I lost the notes now. Great. Great. All right, everything right side now? Okay, good. Twitch is a lot easier. All right, so we okay with how we found the time it takes for him to get back to shore? So again, use the period equation, right? Plug in the length of the string there, and then recognize that it takes half the period to swing there and back, so you get 2.7 seconds. Now, they want us to find the maximum tension in the rope. Well, where's the maximum tension in the rope going to be? Well, it's going to be when tension, right, is pulling upwards the most. Well, at that point, it's going to be your equilibrium position, right? If we were to say, look at a free body diagram of this scenario, right, you've got Josh, you got the force of tension upwards, you've got his weight downwards, right? So that'd be now this guy is moving in a circular path, right? In which case, what kind of motion do we have? Well, we've got centripetal motion, right? He's moving in a circular pattern. So if we want to find the maximum tension in the rope, right, we've got to go back to our net force equation, which if we're looking at it in terms of centripetal motion, right, the net force is equal to mv squared over r. Well, our net force here, if we look at our free body diagram, right, would be your tension minus the gravitational force. So force tension minus gravity is equal to mv squared over r. Right? Or if we rearrange that equation, I'll box it here so it's extra clear. We get that your tension force, just try to get focus, is equal to mv squared plus mg. Well, we've got V, right? V is 2.5 meters per second. We've got M, the mass of Josh is 65. And we've got R, right, which is the length. I'll pull this back up so you guys can see it. 2.5 squared times 65 divided by 7.2 plus 9.8 times 65. And we get a tension force of 693 newtons. We okay with that? Right, it's just like that last Tough Tony problem we did where he was swinging on the pendulum after that candle burned through. Questions in chat? Are we good? All right. So let's move on to mechanical waves. So you've got two different types of waves, right? Waves can either be electromagnetic or they can be mechanical. So if we're talking about an electromagnetic wave, you're talking about things like light or radio or X-ray, gamma, UV, infrared. Those are all of your electromagnetic waves, and they're all waves that travel at the speed of light. Right? Those are the waves that enable us to know anything about the solar system, really, right? How do we know anything about our planets or what's out there? Well, it's by observing the electromagnetic waves given off, right? Light allows us to see a visual representation of the planet. Um, the ultraviolet radiation of certain planetary bodies might give us a temperature, right? So we use the electromagnetic spectrum to, determine what's out there surrounding. Mechanical waves, on the other hand, mechanical waves require a medium through which to move. And by medium, we mean stuff, right? There needs to be something that these waves travel through, whether it's air or water or the ground. There needs to be substance for this energy to be transmitted. And that's all that waves are. A wave is energy, right? So when we're talking about mechanical waves, you're talking about energy being passed from particle to particle to particle within a medium. And this medium, it's going to experience some sort of disturbance. It's going to vibrate in one of two ways and then transfer the energy to the next one. That one's going to vibrate in one of two ways. It's going to transfer the energy to the next particle. That's going to vibrate in one of two ways, transfer to the next one, and so on. And these particles within the medium, right? They're going to vibrate in such a way to where, well, we're talking about simple harmonic motion, right? You're talking about things moving between two amplitudes. It's the same thing with the waves with the atoms of the medium, right? They're going to vibrate between two amplitudes. The energy is going to be passed on. Now, because a wave is, well, actually, before we get into that, your typical example of mechanical wave, and it's going to be the type of wave we're going to focus on for the majority of this unit, is your sound wave, right? So sound waves need mediums through which to travel, whether you're talking about ground, water, or air, right? So whenever you see these these space movies where you've got yourselves your spaceships and they're flying around going pew, 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 pew. Well, that's not very realistic, right? Because in space is a vacuum. There's no medium through which sound can travel, being a mechanical wave, right? So therefore, any sort of action in space would be dead silent. That's one thing to keep in mind. Sorry, Star Wars fans. Now, keep in mind, because a wave is energy, right? A wave has to have a source. Right? Think back to conservation of energy. Nothing can magically appear or disappear, right? The universe is not a magical place. So when we're talking about a source of a wave, right, it could be anything from, say, if you're talking about sound wave, you drop your pencil on the ground. Well, the pencil hits the ground. There's some disturbance in the air molecules around that collision, and those pressure waves that are generated are what we call sound. Right? And those pass from air atom to air atom as they oscillate back and forth until it reaches your ear. You hear the sound of the pencil hitting the ground. If we're talking about, let's say we've got ourselves a pond and it's a perfectly clear day. There's no wind. Well, no waves are going to generate in that pond, right? The only way for a wave to suddenly appear in that pond is if someone, say, takes a stone and throws it into the middle of the pond, or you put your hand in and you push on the water, right? So waves need to have a source, right? Energy cannot come from nothing. So there has to have been something originally that started this transfer of energy. Now, when we're talking about mechanical wave speed, right, which we're going to use v as the wave speed, depends entirely on the properties of the medium itself. So don't fall into the trap that a lot of people fall into, that frequency indicates speed. Frequency and speed are totally independent, right? Something can have a huge frequency and a low speed, or a low frequency and a high speed, right? So those are two separate things. It's entirely dependent on the medium through which it travels. So for instance, like if we're talking about sound, sound travels a lot faster in ground than it does in air, right? If we're talking about, say, waves on a string, it's going to depend on things like tension, the density of the string, things like that. So it's all dependent on the medium, right? And one other thing to think about is the only thing that's being transferred when you're looking at waves is energy. The particles of the medium themselves, they do not travel. What they do is they oscillate in place. So let's say you've got yourself, like, let's say this is the surface of the ocean, right? And you've got a wave passing, right? Maximum amplitude, negative amplitude. Then they're going to return to their original position as that energy moves on to the next particle. So the actual atoms of your medium return to where they started, and only the energy is transferred. So if we want to talk about in terms of sound, think about it this way. Let's say that, well, let's have two people talking. You got Jack on one side, you got Jill on the other. Jack is talking to Jill. Well, what happens? His vocal cords vibrate, right? That's going to cause an oscillation within the air, within the throat, right? And that energy is going to be passed from air atom to atom to atom, right? Each atom is going to oscillate back and forth and pass the energy on to the next one until it finally reaches the other person's ear, right? Their eardrum is going to oscillate upon receiving that energy. And it's going to translate into an electrical signal in your brain, which is going to tell you what you hear. It's not that sound particle or that air particles get energy here, and then that one particle just floats out from my mouth to someone's ear, right? That's a good way to spread, well, gross things, right? So it's only the energy that's transferred, not your mechanical waves. They fall into two different categories, right? They can either be transverse or they can be longitudinal. Now, sound, we're going to find, is going to be a longitudinal wave, whereas your transverse waves are things like, let's say you take yourself a jump rope here, like in this example, and you move your hand up and down. Well, what are you going to do? You're going to generate a wave pulse that moves down that jump rope. So your transverse waves, you've got motion of the medium that goes perpendicular to the actual direction of the energy flow, right? Because the energy flow is in the direction of the wave speed here, right? Whereas the rope just goes what? It goes up, it goes down, then it comes back to its original position, right? So you've got a perpendicular relationship between the motion of the medium and the flow of energy. Whereas your longitudinal wave, you have motion within the medium that's parallel to the flow of energy. So for instance, let's say you take yourself a slinky and you push on it back and forth. Well, the slinky is going to oscillate forward and backwards and then return to where it originally was. But the energy moves through the slinky parallel to the actual direction of travel or direction of oscillation of the slinky itself, right? So transverse waves, you have perpendicular relationship between the flow of energy and the movement of the medium, and longitudinal, you have parallel relationship between the flow of energy and the motion of the medium. And again, if you got any questions, jump in chat and let me know and I'll stop. All right, so let's say we've got spectators at a sporting event and they're doing the wave. As shown in, well, if you look at the book, you'll see that photo, but you should know what the wave looks like. Is the wave at a sporting event a transverse or a longitudinal wave? Well, think about it. Let's say this is a seat in the stadium. Which way does the energy move throughout the stadium? Well, right around the stadium itself. which way do the people move? Well, the people move up and down, right, as the energy flows around the stadium. So you've got yourself that perpendicular relationship between the flow of energy and longitudinal wave in a stadium. Well, everyone in their seats would just go back and forth, right? So it's all about the motion of the particle itself compared to the motion of the energy. All right. Now, we want to look at waves on strings as their own separate kind of entity. And keep in mind, the speed of the wave on a string is going to eventually, when we look at the next equation, affect the frequency at which that string will vibrate. All right. So if, let's say, you play guitar, what affects the sound on a guitar? Well, think about it this way. How do you tune a guitar? Well, you've got those adjustments up on the neck, right? Those change the tension within the string of your guitar, right? Notice that if we look down here, tension. So I actually probably should change this in the notes, but this here, this T is tension, not period. So the tension, right, affects the speed of the string, right? So that's why you tighten or loosen your strings there. Now, what else would you notice about a guitar? Well, guitars, if you look at the strings, they all have different linear densities, right? Meaning they all have different thicknesses, right? So that affects the speed of your wave going down the guitar as well, right? So that's how your basic guitar works. Now, keep in mind, again, we're talking about waves, we're talking about energy, we're talking about something that is dependent solely upon the properties of the medium. So, again, when we're looking at the speed of a wave through a string, right, it depends on tension, it depends on linear density. And all linear density is the mass to length ratio of that string. And again, linear density is going to be represented by the Greek letter mu, right? Same variable as friction was. And again, all it is your mass to length ratio. So notice if we're looking at our equation here, right? The higher the tension, the greater the speed of the wave in the string is going to be. The lower the tension, the lower the speed. The greater the linear density, the lower the speed of the string would be. Well, why would a greater linear density decrease the wave speed? Well, think about it. If you've got greater linear density, what do you have more of? Well, you've got more inertia, right? So it makes sense that the more linear density a string has, the less, the lower this wave speed on that string is going to be. So let's take a look at an example here. So we're told that all spiders are very sensitive to vibrations. It will sit at the center of its large circular web and monitor radial threads for vibrations created when an insect lands. Assume that these threads are made of silk with a linear density of 1 times 10 to the negative fifth kilograms per meter under a tension of 0.4 newtons, both typical numbers. If an insect lands in the web 30 centimeters from the spider, how long will it take for the spider to find out? Well, they've given us our linear density, right? Linear density measured in kilograms per meter. We're given the tension. So if we want to know the wave speed, right, we've just got to plug it into this equation right here. So the speed of the wave on the string is going to be the square root of the tension over the linear density, which would be the square root of 0.4 newtons over 1 times 10 to the negative fifth kilograms per meter. So we get a wave speed of 1.4 divided by 1 second e negative 5 square root answer. We get a wave speed of 200 meters per second. Any questions on that calculation? Are we okay? All right. So we're now told that if we want to know how long it will take for the spider to find out, given that the spider is 30 centimeters away from the insect, how are we going to do that? Well, remember, we've said that wave speed is entirely dependent on the properties of the medium. Now, are the properties of the medium of this spider web equal throughout? Yes. So if the properties of the medium don't change, what do we know about the speed of the wave moving through that medium? Well, the speed of the wave does not change, right? This wave travels at a constant speed as long as it travels through a medium that does not change. Which means if we want to find how long it's going to take for that spider to know it's caught its lunch, we go back to the first equation we've ever had, right? Where speed is equal to distance over time. Right, so we know that the spider is 0.3 meters away. So 0.3 meters divided by 200 gives us a time of 0.015 seconds, right? Or if we want to put that into milliseconds, it'd be 1.5 milliseconds. Right, to gut check your answer, right? Does that make sense? Well, yeah, right? Shouldn't a spider or a spider's web or a spider have evolved to create a web in such a manner that it should be able to nearly instantly recognize when it's caught something in its web, right? So a very small time is perfectly appropriate there. All right. So it's a good conceptual question. Suppose you shake the end of a stretched string to produce a wave. Which of the following actions would increase the speed of the wave down the string? There may be more than one correct answer. If so, give all that are correct. So I'm going to give the people watching here a couple minutes to look through these options, see what they think. All right, let's go through these one by one here. So we want to know which one of these would increase the speed of the wave. So A says move your hand up and down more quickly as you generate the wave. Well, that's going to have no effect. Well, why not? All you're doing is you're changing the frequency of the wave, right? If you simply move your hand up and down more quickly as you generate the wave, you're just increasing the frequency. And again, speed, wave speed, has nothing to do with frequency, right? So all you're doing is increasing the frequency. You haven't changed the tension or the linear density of that string. Therefore, you have not changed the speed itself, right? So again, this and B, whereas B, or sorry, no, never mind. Just this one, right, is trying to trick you into thinking that frequency and velocity are tied together. But again, your wave speed is entirely dependent on the medium through which it travels, so increasing the frequency has no effect. So A is false. So B, Move your hand up and down a greater distance as you generate the wave. Well, all you're doing there is you're increasing the amplitude of that wave. Have you changed the string's properties at all? No. You haven't changed the wave speed then. All you're doing is increasing the amplitude of the wave, meaning giving the wave more energy, right? But you haven't changed the actual properties of the string itself. The wave speed on that string remains identical. All right, so option C is use a heavier string of the same length under the same tension. Well, if we use a heavier string of the same length, we've increased our linear density. If tension remains identical and you've increased linear density, well, you're decreasing the wave speed. You've changed the speed of the wave, but we're looking for solutions to increase the speed of the wave. So part C would just decrease it. Would decrease your linear density. If your linear density goes down and tension remains constant, well, the wave speed, right, would increase. So we know that D for sure would lead to an increase in your wave speed. All right, E gives us the option of stretching the string tighter to increase the tension. Well, again, let's go back, look at our equation. If we increase the tension, we've increased that wave speed. So E would be a good solution. Now F says we can loosen the string. Well, if you loosen the string and decrease your tension, your wave speed goes down. So yes, you've changed the wave speed because you've changed the physical properties of the string, but you haven't increased it, you've rather decreased it. Any questions there? Are we okay? Now, we'll hold off. No, actually, let's quickly go through this because we got time. Now, your primary equation for waves is the wave equation. Right? And the wave equation tells us that the speed of the wave is equal to the frequency times the wavelength. But again, don't let this equation fool you into thinking that frequency dictates the speed of the wave. The wave speed is dictated only by the properties of the medium. So basically what this equation tells us is that V, your wave speed, is locked in by the medium through which it's traveled. So a higher frequency simply means that your wavelength goes down. A lower frequency simply means that your wavelength goes up. So changing your frequency has the inverse effect on your wavelength, right? So a change in frequency doesn't change your wave speed. Your wave speed is locked in by the properties of the medium itself. A change in frequency simply changes the wavelength. So again, don't read this equation wrong. Now, F, right, again, is your frequency in hertz. Lambda, that's what this guy is. That's the Greek letter lambda, is the wavelength in meters. Right, so meters per second is your wave speed here. Now, this equation, though, is nothing new. Right, if you're looking at, say, your wavelength, well, your wavelength is traveled in a period of time t, right, your period. So if we look at velocity equals distance over time, in this case, the distance we're looking at, right, is the wave speed, and the time that we're looking at is the period. Well, what's 1 over period? Right, remember that period and frequency are inversely related. So if you have wavelength divided by period, that's exactly the same as saying frequency, well, focus, times wavelength. So all this is a derivation of our first equation we ever learned, right? The constant speed equation. Now, let me pull this up real quick. Let's go to MS Paint. There are a couple vocabulary terms you want to know when we're talking about waves. So let's just draw a wave real quick. That'll have to do. All right. Actually, that's a terrible wave. Let's just freehand it. Yeah, whatever. That'll do. Okay, this dashed line that I'm drawing here, ever so nicely, right? That's your equilibrium position of your medium, right? Meaning that this is where your medium is when it's not wave passing through. Now, this distance here, right, from one identical location on a wave to the next identical location, so say from the peak of a wave to the next peak, that's your wavelength, right? And it takes a period of time, capital T, your period, to travel that distance. Now, this portion down here, right, that's what we're going to call a trough. Right, so the trough is the low point of your wave. Your trough is your negative amplitude. Up here, your high point in your wave, right, that's what we call your crest. Right, your crest is your positive amplitude. Again, this distance here would be your wavelength, and it takes a period of time, t, to travel that distance. So make sure you're comfortable with these vocabulary terms because you're going to see trough and crest a lot in some of these problems, right? So again, your trough is just your low point, your crest is your high point. And sorry for the terrible drawing. And again, your frequency is how many times a cycle happens per second. So in this case, we're talking about how many complete waves occur in 1 second when we're talking about the frequency of a wave. So if we look at this example here, you've got 3 waves traveling to the right with the same speed. We want to know which wave has the highest frequency. They all have the same horizontal scale. So basically what the question here is asking is which one of these waves, which one of these waves has the greatest frequency, meaning which one of these waves has the greatest number of cycles per second occurring? Well, it's easy to tell just by looking at this these 3 graphs. Which one does it have to be? Well, it's got to be B, right? B, you have the most occurrences of something happening per unit time. Questions? We good. All right. So let's say, let's take this example and then we'll wrap this up. Let's say we've got ocean waves. They're observed to travel along the water surface during a developing storm. A Coast Guard weather station observes that there's a vertical distance from high point to low point of 4.6 meters and a horizontal distance of 8.6 meters between adjacent crests. The waves splash into the station once every 6.2 seconds. Determine the frequency and speed of these waves. All right, so basically, it helps to kind of sketch it out. We're told that there is a horizontal distance between crests of 8.6 meters. Well, what does that represent? Well, that represents your wavelength, right? That's the distance from one occurrence of a wave to the next occurrence of that wave. So that distance between your adjacent crests of 8.6 meters is your wavelength. We're told that the waves splash into the station once every 6.2 seconds. So every 6.2 seconds, one cycle occurs. Have they given us frequency or have they given us period? So once every 6.2 seconds. That would be your period, right? Remember, period is seconds per cycle. Frequency is cycles per second. So the period is 6.2 seconds per cycle. So we're given the period of 6.2 seconds. Well, we know period and frequency are inversely related. So if we want to know the frequency is 1 over period. So 1 over 6.2 seconds gives us a frequency of 1.61 hertz. Now, the last bit of information is that they've told us that from high point to low point vertically, there's a distance of 4.6 meters. So if we were to look at all of the information they've given us sketched out, right, it'd look like that. We've got a wavelength of 8.6 meters. We got that vertical distance of 4.6 meters. We've got a frequency of 1.61 hertz. Now, do we need this vertical distance here? No, that's extraneous information. What have they given us? They've given us a way to solve for the amplitude if we wanted to know what the amplitude was, right? Because the amplitude would be half of that total vertical distance, right? The amplitude is from your high point or your low point to equilibrium position, right? So if, again, we're to sketch this out, right, this distance here would be your positive amplitude, and this distance here would be your negative amplitude. So your amplitude in either direction would be 2.3 meters. Right? Again, that's information. Head plug into the wave equation, where speed is equal to frequency times wavelength. So your frequency times your wavelength of 8.6 gives us a wave speed of 1.4 meters per second. Now, what I'm going to do is I'm going to post some basic examples of, for now, don't even think about when things are due. Just work at your own pace. Because we don't know when things are going to be due, right? It's all going to be dependent on when we go back to school. So take care of things at your own pace. Again, I've got my office hours on Tuesdays and Thursdays. So, if you get bored and you want to give a few of these a try and you run into an issue, come in, catch me on Zoom between 2 and 3 p.m. and I'll help you out with those. But again, don't stress about any due dates. Just work at your own pace. And again, just remember that really when we're talking about getting you prepped for this AP exam, because again, we don't even know when the AP exam is going to be held right now. And since we're stuck doing this all online for now, a lot of this is going to be, what you're going to get on the AP exam is a lot of what you're going to be putting into it yourself. So do what you think you need to. Eventually I'll collect all of this at some point, but again, just focus on, work at your own pace. You know what you need to be doing. Okay with that? All right, my throat is dead. I will see y'all tomorrow if you got any questions in office hours. And yeah, stay safe out there. Hasta la vista. End.